In this video, we will learn about nucleophilic aromatic substitution reactions, so often abbreviated as NAS, or actually also referred to as SNAR reactions. So in NAS reactions, the aromatic ring is reacting with a nucleophile, so the aromatic ring is an electrophile, and that's the opposite of the case for EAS reactions, in which an aromatic ring is nucleophilic reacting with electrophiles. When we do NAS or SNAR reactions, what we find is that the substitutions only really take place if there is a good leaving group. And in the case of NAS reactions, good leaving groups are usually going to be fluorine or chlorine. There are other examples, but almost always we'll deal with the halogens, specifically fluorine and chlorine. There are two main types of mechanisms through which NAS reactions can take place, and they are going to sound very similar to each other. The first of these is called an addition-elimination reaction, and the second is the other way around, so elimination-addition. So let's start off looking at the addition-elimination mechanism. This mechanism is essentially the exact same as the mechanism you would draw for performing a carbonyl substitution reaction. So here's an example reaction. If I take fluorobenzene, react it with sodium methoxide, at appropriate temperature, I can get that substitution to take place, where the fluorine was a leaving group and the methoxide here is my nucleophile. So of course the mechanism starts off like this. We have a good nucleophile, we have an okay electrophile. You should anticipate that maybe this is not the best electrophile in the world because that pi bond is part of an aromatic system. Nonetheless, since the reaction does take place, we know that it's possible for something like this to happen. That gets us to the intermediate, which is now a carbanion intermediate. So in the addition-elimination mechanism, the intermediate is a negatively charged species. Of course, this is not very stable. This should be very high in energy. And just like in EAS reactions, we tend to want to reform that carbon-carbon double bond in order to recreate the aromaticity that was lost. And so that is exactly what happens. This will collapse down, and we have two leaving groups to choose from. Fluorine is the better one, and so the fluoride is the thing that leaves. So if you think about this as a tetrahedral intermediate right here, you should immediately see that this looks just like a carbonyl substitution reaction. Overall, that should get you to the product and, of course, the leaving group fluoride. So just to be clear again, this mechanism takes place in two steps. First, we have that nucleophilic addition to the pi bond, and then second, we have that beta elimination or collapse of the tetrahedral intermediate to reform the carbon-carbon double bond. The second mechanism, or elimination addition here, it goes through a benzyne intermediate, and so because of that, this mechanism is also often called the benzyne mechanism. An example of that reaction is here. So if I take chlorobenzene, react it with sodium amide, where amide is referring to NH2-, that can overall get you to a substitution to make this arylamine. The mechanism proceeds like so. So first, we have to perform an elimination, which means we need to, if you look up here, we create a pi bond in this process. Same thing here, we need to create a pi bond. The way this happens is that we have a strong base as our reagent here. So the amide is both a strong base and a great nucleophile. And to perform an elimination, that would look like this. So this case, we have the leaving group leaving in the first part of the reaction. That gets us to the intermediate here, which looks like that. That is called a benzyne right here. And it's important to remember that you can draw a resonance form that looks a little bit weird, but has three double bonds in a row, but at angles to each other. Those two drawings are the same molecule, of course. Both are going to be benzyne in this case. This, you should anticipate, is a very unstable molecule because we are forcing what are sp hybridized atoms to be nonlinear. The instability of benzynes makes them basically impossible to ever isolate, and so as soon as they are formed in a reaction, they are going to react in the next step. Benzynes themselves tend to be electrophilic in the way that they react, and so what we have now is the possibility of having a second molecule of amide come in. I'm going to have it attack the left resonance form there and push a pair of electrons out. So this, even though it's on a triple bond, should look like addition to a carbonyl. We're attacking one atom right here, pushing a pair of electrons to the other atom of that pi bond. That overall gets us to this carbanion species. This carbanion can then deprotonate one hydrogen from the ammonia, either the byproduct right here or the initial solvent molecule, and that overall will get us to the product. So again, just to be clear, what we're doing here is we're first doing a beta elimination. So we're deprotonating and at the same time eliminating a chloride. In the second step, we're now adding to the pi bond. And then finally, because of the order that this all takes place, we need to reprotonate the anion. That gets us to our final product. A question that often comes up is, well, that second mechanism, the benzyne mechanism, doesn't look great because of the formation of a benzyne. So how do we know that a benzyne is actually being formed? And that's a good question. A lot of the evidence is indirect, but it's still very strong evidence. So let's start off just again with our example reaction. So we know that this substitution takes place, but this reaction itself does not provide any evidence for whether the mechanism goes one way or the other, right? So I could draw equally valid addition-elimination mechanism or benzyne mechanism, and you would have a hard time trying to disprove either one of those. And so experimentally what chemists did is to run some experiments with different structures in order to see if they could try to make it so one of those reactions was impossible. So the first kind of big piece of evidence for the benzyne mechanism was that if you take the dimethyl chlorobenzene here, where you don't have a hydrogen that you can eliminate with to make a benzyne, and try to react it with sodium amide, then there's actually no reaction at all. So you don't get any substitution taking place if you try to mix these two reactants together and run the reaction. And so that's really strong evidence that there is no direct addition of the nucleophile to the ring first. Right? So this suggests that the first step should be an elimination, the benzyne mechanism. A second experimental piece of evidence is that now if you take just a methyl chlorobenzene here, and run that same reaction, what you actually get is not just one product, but two different products. So you don't just get substitution directly where the chlorine is, you also end up seeing some of the nucleophile adding to the position where the chlorine is not. And the reason that happens is because we are going through an intermediate that has electrophilicity on both atoms, right? Because when we make a benzyne, we are creating a new pi bond that's electrophilic, and either of those reaction sites could be used when colliding with sodium amide, and so either of those products could be formed. And so taken together, these two pieces of experimental data provide pretty strong evidence for the benzyne mechanism taking place. The natural follow-up question to all this then is, well, given a potential nucleophilic aromatic substitution reaction, how can I tell which of these two mechanisms is more likely? And there's a few things we can look for. So addition-elimination NAS tends to generally involve very electron withdrawn rings, so very electron poor rings, and they can involve either weak or strong nucleophiles, so the nucleophile doesn't really matter. The way we get the reaction to happen is to have really good electrophiles. A good example of that is right here. So this is a dinitrochlorobenzene. The nitro group is extremely electron withdrawing, and so with two of them here, that really activates this ring for NAS reactions. And so even a weak nucleophile like a neutral methylamine here is able to react. This particular molecule is actually very important because it and the fluoro analogous compound are used very often for labeling biomolecules. And it turns out that if you react this with any NH2 containing molecule, so that's the vast majority of our biomolecules, you get something kind of fluorescent or colorful in the end, and that's used to trace biomolecules in all sorts of biochemistry experiments. For the benzyne mechanism, or the elimination-addition NAS reaction, that's more likely to take place when you have a very strong nucleophile that's also a very strong base. And in general, we will see the benzyne formed when the ring is relatively not electron poor. And so an example of that would be this reaction here, where I have this chloromethylbenzene here reacting with sodium amide. But if I look at this, I recognize that I have this negatively charged nucleophile that's very, very basic because it's a negatively charged nitrogen. And then I see that my aromatic ring here doesn't have very strong electron withdrawing groups on it, but rather it has an electron donating group on it in addition to the leaving group. And so those two pieces of information together point me to the elimination addition NAS. Now let's take a deeper look at some aspects of NAS reactions. A question that always comes up when first learning organic chemistry is, how electron poor is electron poor enough, or how electron rich is electron rich enough. So what I'm going to show you now is a very qualitative view on how fast addition-elimination NAS reactions can take place for a molecule which is an aryl chloride reacting with a nucleophile. So let me show you a table of 3 reactions here. And so what I'm showing you is different electrophiles reacting just with a generic nucleophile. And I'm giving you kind of a temperature at which reaction rate is considered reasonable. And so reasonable means that the reaction would be done within a day's work. So in general, for an organic chemist, that means, let's say, 4 hours, because it takes a little bit of time to set up the reaction, 4 hours to run the reaction, and then a few hours afterwards to clean up. So for a molecule like this one, where I have an electron withdrawing group, a moderate electron withdrawing group, a strong electron withdrawing group, and then the leaving group on it, you can expect something like this to react with a nucleophile in an NAS reaction at a reasonable rate at room temperature. So this would be a relatively good reaction that you would expect to happen with decent nucleophiles. If we only have the nitro group on there, so that's the strong electron withdrawing group, but only one of them, then usually you will need to apply a little bit of heat to get that reaction to happen at a reasonable rate. And so the benchmark is this will happen around 100 degrees or so. Finally, you can get much more powerful electron withdrawing groups on there, so things with positive charge on them. And when you have those, then you tend to be able to do your NAS reaction with essentially any nucleophile, weak or strong, at room temperature. And so the reason to keep this in mind is that while we may not always see the exact temperature at which a reaction is run, indications that heat is being added to the reaction mixture are often a sign that you should be able to do what is otherwise maybe a less likely reaction. A second situation that comes up with NAS reactions is that while there's not as much of a concern over selectivity because we know that there needs to be a leaving group at the site of the reaction, there can still be selectivity if you had 2 potential leaving groups in a given NAS electrophile. So for example, this difluoronitrobenzene here, I have 2 different fluorines, 2 different carbon fluorines rather, that I can react at. And it turns out if you run this reaction, you do get a major and minor product, indicating that the intermediates for forming this product are going to be lower in energy. The pattern that we see is that the addition-elimination NAS reaction tends to take place at the CX group that is either ortho or para to the strong electron withdrawing group. The reason for this comes from the stability of the carbanion intermediate, as is the case with all questions about selectivity. So I have those intermediates here, and so if we're looking at them, what we see is that the major product comes from the intermediate where the anion is here, which thus by delocalization would allow us to put electron density there, or all the way out to this oxygen, through resonance of course. So we can do resonance that looks like so. The other intermediate, however, does not have that capability because if I try to draw the resonance forms, I only get delocalization of that negative charge at the highlighted positions like so. So because of that then, this intermediate should be much lower in energy because the electron withdrawing group is able to delocalize the negative charge that's formed in the intermediate. This intermediate is not, so this should be very hard to form. Selectivity is not limited to just the addition-elimination mechanism. In the benzyne mechanism, we also have a choice of 2 carbon atoms to react at, and sometimes we do see selectivity between those 2 carbons. So as an example of that, if you take this bromoanisole here and react it with sodium amide, what you actually end up seeing is that this is the only product that is formed. So you don't get any substitution at the original position of the leaving group. So all of the substitution happens this way. Of course, the explanation for this is going to go back to the intermediates. And again, it's going to be to the carbanion intermediates. So the first step is the same. We're always forming a benzyne. There's only one way to do that. Once we make the benzyne, at this stage, the nucleophile has 2 potential places to attack. You can either attack the upper carbon or the lower carbon. So going there or there. And so if you're looking at this, an important thing to keep in mind is that this negative charge is not part of the pi delocalization here, because that lone pair of electrons is on an sp2 atom that already has a pi bond. So this negative charge cannot be stabilized by resonance at all. That is not the same as the addition-elimination mechanism, where we could get that stabilization by resonance. So again, here, we can't think about resonance, but we can think about inductive effects. And so the major stabilization that is being experienced here is that this negative charge, which is isolated on the carbon atom right here, is closer to the electronegative oxygen atom. And so overall, then, that makes this intermediate a little bit more stable than this one here, because this negative charge is further away from all the inductive effects. And so this is the major intermediate. And so this intermediate is much easier to form. That's the one that leads to the major product observed. So that was a look at NAS or SNAR reactions, in which the aromatic ring is actually the electrophile in the reaction. These reactions can take place through two different types of mechanisms, either first addition then elimination, or first elimination then addition.